Hello, this is my lab report on constant velocity. The purpose of the lab is to observe the motion of some object that is moving at the same speed without changing direction. In my case, I'm using a cart moving on a linear track traveling at a constant velocity. The motion of the cart will be analyzed and my observations will be used to compare the experimental model to the computation model. Here I've listed some of the fundamental physical principles used in this lab. For an object to be at constant velocity, the net force acting upon the object must equate to zero. This means that all forces acting on the object cancel out and the system is at equilibrium, resulting in constant velocity motion. These formulas listed on the slide derived from Newton's second law will be used in this lab to predict the position and velocity of our object at a future time in our computational model. In the results, there will be two different models plotted on the same graph, one experimental and the other computational. With the experimental model, I use Tracker to analyze the recorded video of the cart moving on a linear track to extract the cart's position and corresponding time, allowing me to plot the observed position versus time. With the computational model, I use GlowScript to input the formulas mentioned in the previous slide to predict the position of the cart, allowing me to plot the predicted position versus time. I would also like to note that in the computational model, it's assumed that there is no air resistance and friction acting upon the object. This is different from what we observe in our experimental model because we're looking at the object's motion in the real world where there is friction and air resistance. This is reflected in our results where we can see that the predicted position differs from the observed position on the graph. As you can see in this video, the system is the cart and the surroundings is everything else surrounding the system, which includes the earth, the track the cart is traveling on, and the person pushing the cart. These surroundings interact with the system through gravity, friction, and the initial push force. In our experimental model, I used the video of the cart and tracker to plot the object's position as a function of time. The cart moves from left to right going in a positive x direction, resulting in an upward sloping graph of position versus time. The data points from tracker is used to plot the experimental model of the cart's motion. To make the computational model, I first set the initial conditions in GlowScript. Looking at my data in Tracker, I can see the initial position of my cart at t equals 0 seconds is at 0.0148 meters. As you can see in my code, I set the initial position to match with the one shown on Tracker. In order to get the object's velocity, I use the first 2 points of data from Tracker and substitute those values into the formula change in position over change in time. With those two data points, the velocity is calculated to be 0.0524 meters per second and is implemented into the data. The initial conditions seen on GlowScript match with the initial conditions given by Tracker. As for the object's mass, I didn't edit it as it doesn't impact the calculations of this experiment. And for delta t, the time step in the code is 1 over the frame rate I recorded at 30 frames per second, which matches with the time step seen in Tracker. With the initial conditions established, I'm able to implement the formulas previously mentioned in the introduction to update the object's velocity and position. As I run this code, I'm given the computational model where I can see the predicted position as a function of time. Here's the graph of both the observed position and predicted position as a function of time. As you can see, both models initially share the same slope, aka the same velocity. However, as more time passes, the slope of the experimental model decreases, indicating a decrease in the velocity of the cart. The reason why the cart slows down in the experimental model is because in the real world, there's friction and air resistance which affects the cart's motion. And according to Newton's first law, an object in motion will stay in motion unless an unbalanced force acts upon it. In this case, with the experimental model, the unbalanced force is friction acting against the cart's motion, causing it to slow down. But with the computational model, the velocity remains constant because the predicted positions come from the assumption that there is no friction or air resistance acting upon the cart. Without an unbalanced force acting on the cart in the computational model, the net force remains equal to 0 and the cart continues to move at a constant velocity. Moving on to some discussion questions. What if I made the choice to flip the axes? How would the results change? In my experiment, I chose to have the positive x direction represent the object moving to the right and the negative x direction represent the object moving to the left. If I were to interchange negative x and positive x, I would have a downward sloping graph instead of an upward sloping graph. Despite this change, I would still come to the same conclusions that the predicted model and observed model differ due to the friction acting upon the cart in the observed model causing a decrease in velocity. Now, what does it mean? Is it possible for me to say how many pushes and pulls are added together to give a net force equal to 0 in the case I've observed? The answer is no. Seeing how the velocity isn't constant in the experimental model, we can't say the net force is actually equal to 0 knowing that friction, air resistance, and gravity played a role in the cart's motion. In the real world, it's difficult to have an object move at constant velocity with the existence of friction and air resistance, which can cause the object to decelerate. This differs in the computational model where I can set the net force to be 0 and have a constant velocity. Some possible sources of error include human error and issues with the object itself and its surroundings. With human error, I could have pushed the cart too hard, causing an inconsistent velocity. If you look at the graph, you can see how the observed position is briefly above the predicted position. This could be because the initial push caused the cart to accelerate instead of being at constant velocity. There could have also been issues with the system itself. The cart could have damaged wheels and may have caused it to slow down. Similarly, the cart's surroundings may not have been ideal. The track it was traveling on could have had some inconsistencies like bumps or dents affecting the cart's motion. So what can we conclude from this experiment? An object's motion observed in the real world differs from what is predicted in the computational model due to the forces like friction, air resistance, and gravity that exist in the real world. Though our experimental model and computational model may be similar, they will never exactly be the same.